Let's start by kind of talking about what we're going to be talking about today. We're going to do an introduction to Etherchannel, which seems like a relatively simple topic, and actually it is. But you're definitely going to have to be aware of how Etherchannel works. We're going to take a look at some different use cases. Why would I want to use Etherchannel? We're going to take a look at some of the behind-the-scenes pieces about the load balancing algorithm, maybe what kind of aggregation we're going to be running. And then I'm going to do a little compare and contrast about some of the different types of Etherchannel. Cisco actually supports 3 unique types of Etherchannel. We've got multi-chassis Etherchannel, what is affectionately known as MEC or MCEC sometimes, Stackwise, VSS, and VPCs. And we'll talk about where each one of those might fit and what are some of the considerations. Mike Juba, who's not going to be with us today, asked that we also talk a little bit about some of the best practice standards with some of these. And you'll find that with Etherchannel, most of the best practice standards are going to be primarily dealing with order of operations. How do I configure them so they come up appropriately and so that they can function appropriately. We're going to talk about the negotiation protocols themselves. There's not a whole lot of difference between the 2 different negotiation protocols, Cisco's port aggregation protocol and IEEE 802.3AD, which is the link aggregation control protocol from IEEE. Pre-standard was PAGP and post-standard LACP. How does load balancing work? How can we change the load balancing method that we're using on our particular platform? That is going to be predominantly platform specific, but we'll talk about that. We're going to take a couple of short lessons, as you can see from our discussion topics here, about, I don't actually think it's going to take an hour and a half. I've allocated about 3 hours for this time, even though this says 2, 3, 4.5 hours. I really honestly don't think it's going to take even more than 3 hours to go through this discussion today. So unless you guys have a lot of questions, you want to take a look at some other specifics as we're going through the process. But we will talk about the difference between a layer 2 Etherchannel, layer 3 Etherchannel. We'll take a look at some of the different techniques for aggregating the bandwidth of the physical links and so on, right? Now, when it comes to Etherchannel, there are some different terms that are used to describe Etherchannel. For example, you might have port channels. That would be a description, channeling or channeling protocol, link aggregation, NIC teaming. But in the end, Etherchannel is the term that Cisco has coined to become kind of the standard term used to describe, even if you're not technically using in any case, whether it's fiber or copper, it would still be predominantly an Ethernet protocol aggregation anyway. We'll talk about 802.3AD, like I said, and so on. Now, when it comes to Etherchannel, there are essentially 2 major components to Etherchannel. Let me pull up my little notepad document so we can take some notes here. So there are 2 major components to Etherchannel. This is what we tend to focus our attention on when we're discussing Etherchannel. There is the port channel interface, which is your logical component, and then there are the member interfaces, what we call member interfaces, which are essentially the physical links that are part of the particular link bundle. So these are the physical interfaces that are part of the bundle. Can't type. All right, and that's what we're going to focus our attention on. Now, there is a consideration when it comes to configuring these 2 key elements. And by the way, this applies to both layer 2 ether channels, and it applies to layer 3 ether channels. We still have the same concepts. Now, the ultimate goal of any kind of ether channel configuration is to hide essentially the member interfaces from the upper layer protocols. Now, we say upper layer protocols, but I mean, in reality, we're really trying to hide the member interfaces from one protocol, which is spanning tree, right? Spanning tree is going to see one 2 gig link instead of maybe 2 different 1 gig links in the case of a bonded ether channel. And this is, even though there are some other protocols that can be affected by ether channel, things like VTP and you know, even some routing protocols if I have routing over a layer 3 ether channel. But the predominant use in the case of our redundancy domain is to hide the individual member interfaces from the spanning tree protocol, because spanning tree will, you know, provide you guys active and passive forwarding elements, but we want to be able to use both links as we move from, say, our distribution layer to our core, or our access layer to our distribution layer. We want to have active forwarding instead of that active standby forwarding. All right. So even though our physical design might look something like this, let me pull up my putty.
Hey, Scott?
Yes, sir.
I'm not seeing your screen.
Oh, you're not seeing my screen? Oh, hold on one second. So when we have, let's say, and we'll talk about really the kind of restrictions that we want to take a look at when it comes to bundling different links together. But if I have SW1, for example, here, and SW2, obviously from a physical standpoint, we have these 2 links. Maybe this is 0.1 and this is 0.2. But from a logical standpoint, we want that to look like one individual link, or one aggregate link, if you will, from our layer 2 domain. And that's really the ultimate goal of Etherchannel. Even though it's going to provide us other functionality, right? Etherchannel is going to provide redundancy and maybe even some aggregate bandwidth capabilities. Ultimately, we're trying to make it so that all of our layer 2 paths and our physical paths are available to us to provide routing or switching over all the links at the same time. The member interface get configured, member interfaces themselves get configured and entered into that channel process. So instead of spanning tree, you know, operating on these individual interfaces here, spanning tree is going to operate on the logical port channel interface. The MAC address table is going to look like it's tied to the port channel interface, and so on. All right. What are some of the pros to this process? Certainly one of the pros to configuring this process is the fact that we have the ability to kind of provide a cheap incremental upgrade option if we want to have additional bandwidth between our locations. We ran into a situation like this recently with a client where they have some laser optimized multi-mode 10 gig fiber between their facilities, between the buildings. And we said, well, you know, ideally what you should really do is you should generate or create this 40 gig link between your stacks, as opposed to just using, you know, individual, you know, 1 gig links or 10 gig links or whatever. I mean, obviously the multi-mode cable that's going to run between the buildings is going to support that capability of running 40 gig, but the SFPs and the modules and the interfaces that are required on the 3850s, or in this case 3750 stacks that this client had, were cost prohibitive for this particular customer. So the alternate solution was, let's go ahead and just get the 1 gig interfaces, and then we'll just bond 8 fibers together. And that'll give us at least some semblance of 10 gig communication between the locations. I mean, that can be extended to 2 10 gig links, for example, is cheaper than maybe an individual 40 gig link or a 100 gig link. So this could provide you kind of an incremental option to do the upgrade. Obviously, as you guys are aware, you guys have been through CCNA, you've been through CCNP, so you know that the whole purpose of Etherchannel is to provide us the ability to add redundancy at the data link layer. And it creates this kind of a more robust architecture that spreads our failure domain across multiple physical entities, whether it's physical interfaces that exist on a local switch, or if it's in the case of a multi-switch ether channel like a VSS or VPC, spreading it across multiple physical switches themselves. All right. Now you are sacrificing throughput in this particular case. There's a lot of misconception about whether or not an ether channel will actually provide you throughput. So let's say, for example, I take 4 10 gig links and I bond them together to create this logical 40 gig link. Well, actually, you're not really creating a 40 gig link in that case. 4 10 gig links or lags are not going to equal a 40 gig pipe. And that's because the traffic flow itself can never exceed the bandwidth of whatever an individual link is. And we'll talk about this from a load balancing perspective. Now, that's not to say that you're not going to get an additional benefit of bandwidth, because in the load balancing algorithm, we're going to utilize all 4 links at the same time, not necessarily on a per packet basis, but on a per flow basis. And if the flows can be distributed in an adequate load sharing process based on the load sharing algorithm that you decide to use, then you are effectively getting more bandwidth, right? Because if you try to put the same amount of data across a single physical 10 gig link, you might see saturation, or you might see some issues processing that data. So even though the individual or the overall ether channel speed can't exceed the maximum speed of one of the individual members in the group, you're still going to get the benefit of having multiple members, all right? This applies, by the way, to all types of ether channel configurations, even if they're not quote-unquote ether channel. So like a PPP multi-link where you're bonding a bunch of 1.544 megabit per second circuits together, you're still going to be limited to that overall circuit speed rather than an aggregate circuit speed that you might assume. All right. Link aggregation does support load distribution, but it doesn't do true load balancing. And that's definitely one thing that I'm going to talk to you guys quite a bit about in this discussion, because I want you to understand it's not necessarily something you need to understand for the lab. Certainly it's something you need to understand for the written exam, but is how does that load balancing algorithm work? Now, it's going to be predominantly based on the physical platform and how the physical platform decides to do the load balancing, but you're going to get similar load balancing algorithms in different platforms. So we're going to talk about that, but you're never going to truly get, even though mathematically you try to assume that, you're never going to get like a one-to-one-to-one load balancing solution with ether channel. It's just something that just doesn't exist, all right? And we're going to talk about how we track the load balancing, how we can make changes to the load balancing algorithm, and I'll even discuss a little bit about, how you can choose the best load balancing option based on the type of traffic that you're seeing across a particular ether channel, all right? There's also some great documentation on Cisco's website. I'm going to show you guys that a little bit later on. I'll actually save those documents, maybe as part of this discussion, I'll go ahead and proactively save those documents, but there's some CVDs on LAN redundancy and enterprise class redundancy specific to VPC and ether channel, all right? I'm sure there's one on VSS as well, but all right. So what are you going to be responsible for knowing for the written versus what are you going to be responsible for knowing for the lab, all right? Now, we focus a lot of attention in our discussion today on single chassis ether channel as opposed to multi-chassis ether channel. You will not have to configure VPC or virtual port channels or virtual switch stacks in the CCIE lab. Your focus is going to be configuring a single chassis ether channel. It's going to be one of your core layer 2 configuration pieces. However, on the written exam, you're definitely going to have to know about how do I configure multi-chassis ether channel? All right. So ether channels can, what we're doing with an ether channel, and this is really the ultimate goal, is we're doing something called fate sharing at the access layer. Right? Let's say, for example, you have servers in your enterprise, and those servers have redundant power supplies, they have redundant NICs, but they don't necessarily have redundant connections to the access layer. All right? This is pre-ether channel, okay? So all of this redundancy that we have built into our server is lost because we don't have the appropriate redundancy built into our access layer design. Now you might have multiple NICs on the server, but those NICs are not configured in a bonded fashion, right? We're not doing any kind of NIC teaming. One NIC would be forwarding, the other NIC would be simply there to fail over to in the event that the upstream access layer switch fails. So the single point of failure of the server in this case is its fate in the access switch's operation. So what's the solution? Well, the solution is to basically just use two different switches. And that's actually a pretty common solution in a lot of cases, to go ahead and just use two different switches up to the access layer and then have two different links from the server up to the access layer. But the problem with that particular solution is you're running again in an active standby type of scenario where only one link is active when you go and talk to the access layer. NIC cards themselves, network interface cards on the servers, they don't actually do active communication natively. They operate essentially on the protocol stack, just like any other host would, meaning they have a static MAC address or a burned-in MAC address, and they communicate based on that. And they have routes that are tied to those physical interfaces based on their layer 3 domain membership, right? So 50% of the available bandwidth is all you're going to get. And if there is a failover event, if there's some sort of fault, the fault isolation is okay, but the failover is slow, and we're going to maybe obviously lose any kind of open sessions that we might have and so on. So essentially what we need to do is we need to be able to trick the server into running some sort of link aggregation. All right? We have to form a logical chassis between two different physical switches. Now again, I'm speaking in this case from the perspective of multi-chassis ether channel or some sort of multi-chassis design or virtual switch type of design. That way we have 100% of the bandwidth that can be used. That'll provide us a faster failover and it will provide us additional bandwidth. All right, so from a perspective in this case, we're talking about a physical diagram that might look something like this. Maybe we even have some sort of ether channel between those switches. So SW1, SW2, and then on the server side, we have our virtual ether channel, right? Now this can be done in a couple of different ways. We're not talking about stack-wise in this case. All right, I'm going to talk a little bit about the stack-wise ether channel design in a little bit. We're talking about some sort of either multi-chassis ether channel, some sort of VSS, virtual switch stack, or in the case of the Nexus 7K products or the 5K products, some sort of VPC design, where you have a peer link between the two switches. That peer link is established over those two links in between, and then we have some sort of virtual port channel configuration that allows switch 1 and switch 2 to communicate to each other. Now, our focus in this discussion, quite frankly, is about what we're going to see on the lab, not on the written exam. If you guys want me to later on go through a discussion about how to do VPCs, like on a Nexus 7K, I mean, I suppose I could do that, but it's not something that you're going to be required to cover when you go into the lab exam. So It's definitely something you're going to need to know for the written. There's no doubt about that. And I'm going to provide you some documentation that I think is, and this will be kind of one of your first homework assignments, but I will provide you some documentation that will give you some information about that configuration, the VPC/PeerLink type configuration that you see on the 7Ks. All right, now from a logical standpoint, this is just going to look like a switch and some sort of bonded link going over to the server. And that's really what we're trying to accomplish here. I think you guys get the idea. Okay. Now we can do this, even though the diagram doesn't really reflect that. We can do this a couple of different ways. Like I said, we can do a virtual port channel. We can do a virtual switch stack, or we can use some sort of stack-wise technology. All right. So we're not talking about, in this case, a single chassis design. Right? Single chassis Etherchannel where you simply have like gig 1 and gig 2 bonded together on the same switch. That's a little bit easier to do than some sort of multi-chassis solution that we might have to deal with. All right? So we have a physical triangle in this case, and we have to make that physical triangle look like some sort of logical point-to-point connection. You know, we want active-active communication across the links, not active standby communication. There are some potential issues, of course. How do I know what direction that I need to send the traffic in, right? What prevents some sort of layer 2 loop from occurring in this particular topology? That's something to definitely consider. How do I manage my MAC addresses, right? I mean, we know already that we can only have one MAC address per port, okay? Assuming it's an access port. So we're only allowed to have one source MAC address exist on an individual interface. Most of our link aggregation solutions are going to be proprietary, and they're going to rely on some sort of synchronization of the control plane functions between the switch. So in this case here, if I'm running, you know, a VPC here, which is what essentially this is, let's say this is 7K and that's a 7K, I'm running some sort of VPC connection. The peer link, in this case, is the link that's providing that control plane synchronization. All right. And there's actually quite a bit that occurs over that link in order to facilitate this virtual port channel configuration. All right. Now, as far as forwarding goes, if we're forwarding the data plane, that's obviously going to have to happen on both members, both chassis or both switches that are part of the ether channel. All right. So if you want to make sure that if a frame is being sent down to the server on this port, that somehow we're documenting that process so that we're not duplicating frames to the server in the event that we need to send multiple frames. All right. Basically, the switches essentially have to agree on how they're going to handle the data plane functions. How are we going to ensure that the traffic is being forwarded efficiently and that, that we're not duplicating effort, either inbound or outbound as part of this configuration. So it does complicate the design and it complicates the use of the upper protocols quite a bit. Fortunately for us, that's all been engineered and designed into the protocol, and we don't really have to worry about whether or not a switch is going to be able to handle that operation correctly, as long as our configuration is sound and we're using best practice configurations. All right. So Cisco supports 3 variations. Like I said, we can do what we call a cross-stack Etherchannel, where you might have a stack of switches. And the way that this works, we'll talk about the 3850s as an example, right? So you've got your modular switches. Well, actually, these are kind of your static switches. And we join those switches together by creating this ring, which is a proprietary physical layer type of ring over these things called stacking cables. So each one of the switches within the stack has an in and an out. And essentially we create this kind of loop, right? In fact, let me draw that a little bit differently because I want to maybe draw it as the way it looks on the in the physical configuration. So you've got port 1 goes to port 2, port 1 goes to port 2 in this case, and then from this switch we go all the way over back to port 2 from port 1. So 1, 2, 1, 2, 1, and 2. So this creates a virtual ring, or actually a physical ring, I guess, in this case, that operates, 400 plus gigs, depending on the model of the switch. 32 gigs for like a 3750 type switch, but a 3850, that backplane can operate up to 400 gigs. Actually, I think it's about 480 gigs if I'm not mistaken. But in any event, we're creating this control plane capability. Unlike a virtual switch stack or a VSS type configuration or a VPC type configuration where we actually create a peer link or we create this communication of the control plane functionality through physical interfaces, but logically, right? In a switch stack, using the Stackwise technology, the control plane is actually synced over the stacking cables. And we create this bi-directional closed loop for communication over these different stacking cables. One control plane, in this case, gets shared on all of the stack members. So each switch, when they're disconnected from the stack, operate their own individual management plane and their own individual control plane. But in the case of a stacking solution, we only have one control plane function and only one management plane function. All right. So it looks, in this case, based on the way I drew it, that this is basically a chassis-based switch, like a modular type switch, like a 6500 or a 4500 type design, where each of the switches now act as a module within that virtual stack. All right. So it looks like maybe these are just individual line cards within our logical switch. In fact, I could make this even prettier by kind of just drawing the box that represents our switch. All right. You guys have worked with this before. I mean, you guys know how Stackwise features work and so on. You can stack up to, 9 members in a switch stack, I believe, up to 9 members in a switch stack. And then you can even do some power stack options as well, where you can have up to 3 switches that are participating in a powered stack. And actually, I think it's 4. I'm 90% sure it's 4. We usually do 3 because we want like a 3, 3, and 3 ratio for power stack. So if I've got 9 stack members in my layer 2 or my switch stack, for my power stack redundancy, I'm just going to split it up evenly across the stack. All right. In any event, it looks like a single switch. All right. There's a stack master. The stack master is what's going to control the stack. And again, this is a physical layer thing. I mean, it's a stacking and Stackwise technology is based on physical platform. So because of that, because it's based on a physical platform rather than a logical platform, that means that basically it's not going to be tested on the lab because everything in the lab is virtual. So you're not going to have to configure priorities for the switch stack. You're not going to have to do any things like renumbering or modifying the stack master or something like that. Okay. The stack from one port on one switch and other ports on the other switch could then be used to form this ether channel. And this is a very, very common configuration. So I've got my other switch here, maybe switch X, And so I'll use this gig link, and I'll use this gig link, and I'll use that gig link. We'll bond those ports together to create our Ether channel. And it's very simple, very, very simple. Now, keep in mind, obviously, if the ring is broken, it's a bidirectional ring, so it could be broken in one direction, but not broken in the other. Each one of these interfaces represents an innie and an outie, if you will. You know, kind of an ingress and an egress type of port. So if the ring is broken, or if half the ring is, you know, the ring loses its continuity, the first thing that would happen would be that the switch would, the ring would convert to half duplex, and you lose half your bandwidth. But if the ring is broken completely, obviously, say for example that this switch disappears, that switch goes down, the Ether channel is going to go down. We'll see this though. In this particular case, the ports will just revert back to independent ports, and we'll let spanning tree do what it needs to do and so on. In this case, spanning tree wouldn't be a problem because we don't have any physical connectivity between the top switch and the bottom switch. All right. Now, one of the other options that we have is like a virtual switch stack. Virtual switch stack is an aggregation option that we have for things like distribution switches like a 4500 or a 6500 or a 6800 series switch, where you might have 6509 number 1, right, and 6509 number 2, and 6509 2. And you've got your different soups here. So you've got your active and standby soup on this switch. You've got your active and standby supervisors, which is your control plane function. And then between them, you have your virtual switch link, which is your Ether channel. Not a physical link, virtual switch link. Now that virtual switch link is going to be created over a physical cable or a pair of physical cables, whatever it might be. But it's still a virtual switch stack. So from the PC's perspective or from a computer's perspective that might be connected to these two switches, it looks like one logical switch. All right. The control plane in this case is going to be synchronized over the virtual switch link. Remember, this is all part of the VSS technology, virtual switch stacking technology. The VSL, that's where all of my control plane functions get synced up. Usually that's going to be some sort of 10 gig connection or a couple of different 10 gig connections that are bonded together. All right. There's still only one control plane in a virtual switch stack. One management plane, just like the stack-wise solution, one active supervisor, and what will actually happen is one of these other active supervisors, depending on who the stack master is, will revert to a secondary supervisor. So you would actually have ASSS. I was going to write that down, but that might look kind of funny. Okay, where you have one active supervisor and then you have two to three backup supervisors. From the perspective of convergence and from the perspective of just basic functionality, even for example for OSPF, an OSPF adjacency with a virtual switch stack, if I'm running layer 3 on this virtual switch stack and I'm connecting this VSS to another layer 3 device, it's still going to look like the VSS pair is going to look like one logical switch. Okay? And there are some specific requirements when you're dealing with VSS and so on. So we get to support things like stateful switchover, SSO, local and standby. So you might have, for example, if this is the master, if you will, in our case, you've got your SSO functionality here between your active and standby supervisor, and then you also have the failover capability when you go to the other chassis that's part of the VSS. Okay, but these are all stateful components and stateful functions. All right, so you could have, for example, you know, some 10 gig ports that get connected, let me draw that on here. So I've got some sort of switch down here that I want to redundantly connect to my core. Well, I could actually have, possibly 4 or 5 or 6 or 7 or 8 different connections, but those links are bonded together, looking essentially like one ether channel. From the receiving side, from the client side, it looks like I'm connecting to one physical device, obviously. That's kind of the whole point of VSS in this case. Okay. Another option that we have, this is a little bit different, is to, in the data center side, is to do something called a VPC, which stands for Virtual Port Channel. VPC. It's actually written with a little v. Let me write it the right way. VPC. All right, Virtual Port Channel. This is going to be reserved for platforms like the data center platforms, the Nexus 5K, the Nexus 7K, or the 9K. Now this is different. This particular configuration is different than what you would see with like a stack-wise Crossstack Etherchannel or a VSS. All right. The control plane is still synchronized. We always have to control or synchronize the control plane. So I've got my 7K here. I've got a couple of interfaces that might be bonded together, another 7K here, and all the control plane functionality is going to go back and forth. Up to this point, though, every other solution we've looked at incorporates the control plane functionality, and it incorporates the management plane functionality. But in this particular case, even though we have a VPC peer link that allows it to synchronize the control plane information and discuss and talk about the different control plane functions, the big difference here is that we have 2 independent control planes and 2 independent management planes. Very, very different. Okay? You might have 2 active soups, 2 standby soups, so you might have an active supervisor here, active supervisor there, and so on. All right? It still looks like one individual box to the client because we're tricking the client into thinking so because of the control plane functionality that's shared across the VPC link, but in reality it's still 2 separate boxes and 2 separate functions. All right? So, one of the choices that you have then when you're trying to decide what's going to happen with Etherchannel is it supposed to be stack-wise? Is it supposed to be VSS? Is it supposed to be VPC? Obviously, these are distinctly different functions. Stack-wise would be kind of the natural way to go, I think, honestly. But there are some limitations to stack-wise. The switches have to be in the same physical rack, basically. And they have to be connected with this proprietary connector, this stack ring connector, between the different switches in the stack. So there are some limitations, especially geographically. I mean, there's no way you could ever form a stack or an ether channel across the stack if the switches are physically located in different locations. All right? Whereas the stack-wise benefit is that it's much, much faster, right? Much faster than, say, a multi-chassis ether channel or whatever, because those solutions are going to be limited to the capability or the interface speeds that you incorporate in the communication. So there's pluses and minuses to each option. VSS and VPC are always going to be connecting only a pair of switches. All right? So the result in that is going to be we're going from a triangular design down to a point-to-point design based on that. Okay? So one of the things that you guys asked me, actually, in the text group is you said, can we talk a little bit about what some of the best practice standards are for configuring this stuff, if we talk about ether channels and whatnot. And what I have to say about that is that there really aren't any necessarily best practice standards when it comes to Etherchannel. There are good ways of configuring Etherchannel and bad ways of configuring Etherchannel, but there's really no best way of configuring Etherchannel. Let me pull up some documents though that might assist in that decision process, because there's only so much, really, frankly, that you can configure in an Etherchannel. Let me see. Why is my browser not opening? Let's see. I think my browser's messed up here. So I did a couple of searches before class started, just to kind of pull out some things that I thought were kind of useful, and I wanted to provide you guys with some of that information. So if you actually just went out to Google and you just did, hey, what are the VSS best practices? You'll actually see VSS best practices. There's actually a couple of different documents that will come up right away based on that search. VSS being just one of the options that we have, right? There's just Stackwise best practice documents, and there's some VPC best practice documents. But probably the one that I think, and this is one that I'm going to suggest that you guys take a look at, is the third one on the list here, which is the Campus 3.0 Virtual Switching System Design Guide. If you're doing a lot with VSS, or you want to learn a little bit more about VSS. In fact, I'm going to save this into our folder. Yeah, I will download the whole document here. And this design guide, it's quite extensive, so I'm not going to suggest that maybe you guys read the whole thing, but certainly maybe skim through it as part of your preparation for the written exam. Not the lab exam, but the written exam. And let me save this file, and I will go back later, and actually let me just do it now and drop this into the appropriate folder for you guys. Let's see here. So let's cut that and go to our Google Drive, class shares, and I will put some other documents here as well. But as we talk about each topic, this is our Etherchannel topic. That's where I'll put the documentation. All right. Now you can see in this document there's quite a bit of information that's available to you. You know, obviously the best practices is one chapter of it. It talks about VSS, virtual switching system design, what is the campus architecture. But this right here, virtual switching VSS recommended best practice, would be definitely something that you would want to probably take a look at as part of the configuration. Why is that there? Can I make that go away? Can I make that go away? Oh well. We're not going to look at this document right now anyway, but this is a good document to take a look at. You know, how do I enable this VSS with loop guard features? What happens if I'm running port fast or BPDU guard? What if I'm running nonstop forwarding and I'm doing some routing over between the switches? You know, what's gonna happen with my IGP protocols like OSPF and EIGRP? If I'm using multi-chassis Etherchannel or ECMP, what's going to happen over the VSL link and so on. So I would definitely take a look at this document and you know, make sure you reference this document. There's a couple of others as well. There's one called the Campus Network for High Availability. Let me see if I can find that one. You can usually just kind of search through it if you do the CVD search. if you go to cisco.com/go/CVD, CVD stands for Cisco Validated Designs. But sometimes these documents can be a little bit hard to find when you're going through the validated designs. So I'm going to do a search for campus network for high availability design guide. And this is another document that it's a little bit older, but another document that's also very, very good. It talks a lot about timers and tuning with regard to load balancing. One of the aspects of this architecture is how do I deal with Cisco Express forwarding. We'll talk about how Cisco Express forwarding breaks load balancing later on. How do I work with spanning tree? And then we've got the design best practice section here again, where you can go through and take a look at best practice configurations for each of these. Designing in the redundancy, how do I deal with asymmetric routing, spanning tree, or spanning VLANs across multiple access layer switches, and so on. So I'm going to go ahead and drop this in as well. And another great reference document. Remember, guys, I'm giving you a lot of information here, but frankly, it's also your responsibility as well to kind of take a look at some of this documentation and familiarize yourself with this documentation related to the topics that we're discussing. So I think that's a really important concept, right? Yeah, are you going to have time to go through a 260-page document? Probably not, but at least skim through it. Skim through it and identify, the high points. This one's not quite as long. It's only about 60 pages, but again, another great document that's out, that's lived for a long time. I mean, it was published in 2008. So this document is an excellent document as well. There is one more. It is called the High Availability Campus Recovery Analysis Design Guide. High availability. And I did actually take a look. This is one of the ones that I had read prior to going into my CCIE lab back when it was the 4.0 version, because you did have to do a lot of physical layer stuff with that. Campus Recovery Analysis Design Guide. And this is a good document as well. That's weird. An error occurred while processing this directive. Okay, looks like this is still available, but I'm not getting the download option here. So you can see in this particular document, they do talk a lot about any kind of layer 3 convergence, but they talk about a lot of topics that we're going to be talking about quite a bit, right? Spanning tree, HSRP, first hop redundancy. But then when you look a little bit further down, there should be a section in here about layer 2 convergence, Etherchannel and such. Now they got some references to some basic Etherchannel, but I thought there was a whole section in this document about Etherchannel. Maybe not. The first two documents definitely important, and then this document can be kind of useful as well. This high availability campus recovery analysis design. I didn't see a PDF version of that, but you can see as a cross reference, we're still referencing the Cisco Campus 3.0 virtual switching. That's really probably the best document. A lot of this is going to have kind of the same information. All right. You are not going to have to know necessarily any kind of multi-chassis Etherchannel, like I said, for the lab, but you're definitely going to have to know where the pieces fit together, right? At what level would I decide to use a VSS with VPC or VSS versus VPC? When would I use a stack-wise, cross-stack Etherchannel? When would I use a multi-chassis Etherchannel, and so on? All right, so you're going to have to know. I suggest, again, scan through the Campus 3.0 document if you have some time. We'll talk a little bit about what our schedule is going to be for the following week and what we can expect to be able to go through and not go through based on my availability for next week. It's going to be a little bit lighter because of family obligations, but I'll talk about that when we get towards the end of the lesson today. All right. So what about the negotiation protocols that exist? All right. Now, the ultimate goal of lag, like I said, is to essentially trick other protocols in our topology into believing that this is a single link, right? There are some pros and cons to using different types of protocols. And we'll talk about the different options that we have with regard to establishing the ether channel. In our next video, we'll take a look at a layer 2 ether channel configuration, and we'll go through some of the configuration scenarios there. I also want to talk to you about a little bit about ether channel misconfigurations as well, and what happens if, especially with spanning tree, if I have ether channel misconfigurations. So the goal is to trick spanning tree to forward both ports at the same time. The risk you have, of course, in this, especially if it's misconfigured, is you can create an infinite loop in the topology. Negotiated protocols like PAGP and LACP can help mitigate this. And we'll talk about the differences between the port aggregation control protocol and the link aggregation control protocol. All right, port aggregation protocol, excuse me, there's no control in there, and the link aggregation control protocol. We actually have another option. We can do no protocol, which is a static, what we call a static ether channel, and that's where we simply specify the mode, in this case to on. Now that's actually not really recommended because you lose a lot of the protection mechanisms that are built into things like spanning tree when you do a static ether channel. But in a lot of cases, a static ether channel is the option you choose because the dynamically negotiated ether channels don't always work as expected. They don't perform as expected. They don't. The ether channel is not formed automatically, as you would suspect, and so on. But that has more to do with the order of operations when you're configuring the ether channel than it does when, say, for example, that you're doing a mode on. All right, we'll talk about the differences there. All right. There is a feature within spanning tree called ether channel guard that's going to help protect against any kind of loops in the topology. I'll talk a little bit more about ether channel guard in a little bit. And for that reason, because you don't want to lose that capability, a static ether channel is not generally recommended. Obviously, PAGP being Cisco proprietary, if you're connecting to a non-Cisco device, or you're trying to do some sort of link aggregation with the server or some third-party device, the preferred method would be to use the link aggregation control protocol, okay? And that's because it's a IEEE standard, 802.3 AD. All right? Ultimately, regardless of the protocol, you're not going to have to know the specific differences with how the negotiations take place. You're certainly going to have to know which pairings of port configurations will result in an ether channel, active versus passive and auto versus desirable, and even on, but you're not going to necessarily have to know the fundamental differences between LACP and PAGP. Even on the written exam, you're not going to have to know that. The load balancing algorithm that we use is not really based on the protocol. It's actually more based on the device itself that's actually creating the lag. All right? The functionality is essentially the same. So as we move into our configuration section, we're going to take a look at how these lags are configured using the channel group command. And I'll run through some different configurations. We use the channel group and group number command, and then we can specify the mode for the particular ether channel. The group number itself is locally significant, and we'll talk all about that as we get into our next couple of videos. All right? If I do decide to use mode on, there's absolutely no negotiation. It's a static ether channel. and the switch just assumes that the other side of the ether channel is functional and it's operating correctly. I'm going to demonstrate how that could cause some serious problems with like spanning tree forwarding and so on. All right. So within the PAGP realm, we have essentially two different modes of operation. PAGP, we have auto and desirable. And in this case, auto mode is, passively waits for the ether channel to form. So it's not gonna send out any negotiation messages to negotiate or activate the ether channel, whereas desirable in this case is desirable mode actively tries to establish the ether channel. All right. So obviously, if I do an auto to auto cut type of configuration, then no channel is going to be formed, and what will happen is that the ports will essentially revert to independent ports, and they'll operate as normal spanning tree ports, and we'll have one link blocking and one link forwarding. Auto to desirable, that will form an ether channel. And quite frankly, if I'm going to use any kind of negotiating protocol, I'm most likely going to be doing something like this, desirable to desirable. If I choose to use PAGP, for example, that's going to form an ether channel as well. And the reason why is because both sides are negotiating. All right. Now with LACP, we have two different modes of operation. We have passive and active in this case. Maybe I should take a typing class. All right. Passive, just like in auto mode, is going to passively wait to form the ether channel. Whereas our active mode, that is going to actively look to form the ether channel. All right, so if I have passive to passive, no channel is going to be formed. And if I have obviously active, well, let's try and follow the same logic here, passive to active, then we will form an ether channel. And if I have active to active, we will form an ether channel. Now on the lab, they might do something, because we see this quite a bit. Cisco loves to do this. They might tell you or give you a task in the configuration section that says, you need to go ahead and connect these two switches together using these three interfaces or these four interfaces or whatever it might be. But you need to do it in a way that ensures the highest level of redundancy and throughput. Okay, so now you're already thinking ether channel. But then they might extend that and say the switch on the left, both switches should be using an open standard protocol to do this. So now they were saying, okay, it's LACP. And then they might even take it further and say the switch on the left should be the one that's negotiating this link, right? And they might word it in a way to where it's very vague, and they want you to be able to interpret what it is that you're supposed to accomplish based on the wording of what they're choosing, how they're choosing to word the argument, right? So you're checking all the boxes. Okay, well, most amount of bandwidth, all active links. That means I need to do some sort of ether channel. Oh, they want an open standard. Okay, well, that means LACP. Oh, they want the switch on the left to be negotiating. That means that the switch on the left should be active and the switch on the right should be passive or something like that. That's a very common scenario. You'll find this quite a bit actually with a lot of the configurations in the CCIE. They don't just simply say create an ether channel. A lot of times they will tell you to do something, but they'll want you to do it in a certain way. And that's And that's where you get the detailed testing, not only on the configuration pieces, but also you're providing an understanding, or you're demonstrating your understanding of the terminology and the theory and how these things work. Okay? All right. As far as comparability goes, I mean, you're going to definitely need to know what's going to form an ether channel, what's not going to form an ether channel. Now, the other thing that they might actually do as part of the test is they might actually even stretch your knowledge a little bit more by forcing you to identify how you're going to load balance across the ether channel, what kind of load balancing algorithm you're going to use. And they might not even give you a load balancing algorithm. They might say, well, given the fact that we have this kind of traffic in the network and these clients are talking to these servers or whatever, make sure you choose the most appropriate load balancing algorithm to be able to load balance between those switches effectively. So we'll talk a little bit about the load balancing piece. Now, that being said, I doubt in version 5 of the CCIE that they would actually ask you something like that on the lab. Certainly on the written, it's totally possible. But on the lab, remember, we're limited to specific equipment. And a lot of the times, the load balancing algorithms that are used in Etherchannel are based on the physical platform. All right, and we'll get into some command line, and we'll take a look at some of the load balancing options that we have in GNS3 and talk a little bit about what the differences are between those load balancing algorithms, and I will give you guys kind of an understanding of how that works, okay? How you actually decide to do the load balancing of the traffic is controlled by the lag driver itself. So it has a little bit to do with the protocol, but it's mostly platform dependent, okay? Now, once we get our ether channel configured, spanning tree and the cam table, and I'm going to show you guys this as well, ARP caches, anything that's being dynamically created that normally would point to individual member interfaces in the process are now going to see that link aggregation group as the outgoing interface. In our particular case, a port channel interface would be the interface for any kind of MAC addresses I might learn, or a show interface trunk, or whatever. Even a routing. If I'm doing OSPF peering between two different switches over an ether channel, and I'm using a port channel interface to do that, the peering relationship would look like it's logically being created over the port channel interface as opposed to the physical member interfaces. So even if a physical member interface goes down, the OSPF adjacency still remains. I'll demonstrate that a little bit later. That'll be kind of a cool thing to look at, okay? So like things like show spanning tree or show port channel, we really shouldn't see any individual member interfaces in those outputs. Assuming that all of our interfaces are participating in some sort of port channel configuration, or channel group configuration, I should say. So that would be an easy way to maybe check, outside of just a show ether channel summary, might be an easy way for you to check whether or not a port channel is functioning or not. You're looking for those, the logical port channel configuration or reference from those outputs as opposed to the physical member interface function, okay? Different load balancing methods that we have depend on the platform, like I said. Typically, you're going to see something like source destination MAC, source destination IP, source destination layer 4, but there's always going to be some sort of XOR operation. In fact, let me talk a little bit about that. Let's go into a switch here, for example, and type in, let's see, and that let me know. But if I do a show ether channel load balance, you can see that I have some options here, all right? For non-IP traffic, for example, I can do source XOR with a destination MAC address. For IPv4, source XOR with a destination IP address. and for IPv6, source XOR with a destination IP address. And right now I'm using source and destination IP load balancing, which would be this option right here. So let me explain a little bit what they mean by that. All right. Let's say, for example, I have, and it totally depends on how many members you have in the channel group. So let's say I have 2 interface members in the channel group. So interface GI01 and interface GI02 as part of this channel group. So I've gone into those interfaces. I say channel group 1, mode active or whatever on each of the interfaces, and that's going to create interface port channel or PO1. All right, I will show you, I'll demonstrate that process to you. So what essentially happens when you, based on the number of interfaces that you create in an Ether channel, is that the switch itself creates interface index numbers, all right, based on the actual interfaces that are participating. Let's see, we got a chat, port channel load balance. Yes, Ken, that is exactly what I was looking for. Config T, port channel load balance. Thank you. I don't know why I was thinking it started with Etherchannel, but if I do a port channel load balance command, you can see I have some options: destination IP, destination MAC, source destination IP pair, source destination MAC, source IP, source MAC. So we actually have in this particular iOS quite a few options when it comes to actually determining what the load balancing method is going to be. But in order for us to figure out what the best option is, we need to understand fundamentally how the load balancing algorithm makes decisions. And that's where the XOR operation comes in. And that's the most important piece to understand out of this. So we'll take a look at that. All right. So let's say, for example, I've got two interfaces that are participating in a load balancing process. Then we're going to create essentially 2 indices. One is going to be assigned to 1, and it's a little bit more complicated than this, but you know, we don't really need to get into the detailed math and you know, the specifics, but I want you to have a general understanding of how the load balancing would work. So let's say I just give this guy an index of 1, and this interface is going to have an index of 2. So if I'm doing, as in the case here, I'm doing source destination IP load balancing. Let's say that a packet is coming from 192.168.10.12 and it's going to 192.168.200.101. All right. So and by the way, whether or not the switch can actually do, a switch does not have to be configured as a router in order to do source destination Ether channel load balancing. It doesn't have to be a layer 3 Ether channel to be able to do source and destination IP load balancing. But some switches may not support it based on the fact that it's IP rather than MAC load balancing. But in this case, this switch supports it. That's the default mode. So what the switch is going to do is it's going to perform some sort of XOR operation to determine which interface index this traffic is going to be sent over. All right. Here's how it basically works. We take the last octet, convert it to our binary value. So that's my 12. And my 101 is going to be 64 plus 32, which is 96, plus my 4, and plus my 1, which is equal to 101. All right, so 64 and 32 is 96, plus another 4 is 100, plus 1 is 101. So now we've got essentially the last octet is converted to binary, and then based on the number of indexes, which is directly related to how many interfaces are part of the Ether channel, we determine the flow of traffic based on the number of interfaces in the channel, in the port channel. right? We'll just call it in the ether channel. So in this case, we have two interfaces, which means that we need two indices, which means we need 2 bits to represent each one, right? I can't represent, actually, I apologize, 1 bit, sorry. 1 bit to represent each index, all right? So that means to say that if I have index 1, anything that results in a 0 will go over number 1, and anything that represents a 1 will go over number 2. Now, what do I mean by that? Anything that represents a 0 will go over number 1, and anything that represents a 1 will go over number 2. We simply do an XOR operation of the last bit of the datagram. So I do an XOR of 0 and 1, which results in a value of 1, which means that that flow, that data will now go over index number 2. Now, let's say that I went from 12 to 100. So now I'm going from 12 to 100, essentially the same thing. I'm going from 12 to 100, but the only difference here is the result of the XOR operation is now a 0. All right, so XOR of 0 and 0 will equal 0, which means that's going to go over number 1, and this one would have gone over number 2. That's essentially how we do this. But what happens if I have more ports in the ether channel? Let's say I have 4 interfaces in the ether channel. Well, if I have 4 interfaces in the ether channel, then that means I need 2 bits to create an index for each interface. All right, so 0, 0, 0, 1, 1, 0, and 1, 1. So this would be, say, for example, index 1, and this would be index 2, and this would be index 3, and index 4, and so on. All right? And we do the same XOR operation based on the pairs, the source-destination pairs. If the XOR operation results in a 0, 0, we're going to send that over the member interface number 1. If it results in a 0, 1, we'll send it over member interface 2, and so on. So, and as you add more and more interfaces to the lag, you're going to need more and more bits to represent the different indices. So, I mean, the most that we can have is 8 interfaces in an ether channel. So that means 3 bits for XOR operations. So we would have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So that would equal 8 interfaces, 1, 2, 3, 4, 5, 6, 7, 8. And we would simply do an XOR operation against the 3 bits to find out which interface index that traffic is going to flow over. Okay? Does that make sense? So, you know, you look at this and you think, okay, well, that should represent a load balancing method. But there's an inherent problem with this method, isn't there? Because what happens if host 12 is sending large data transfers to host 101, whereas host 12 is only sending an email to host 100, right? So you can end up essentially where you have a significant amount of load on one switch. We call this polarization, by the way, in terms of ether channel, where you can essentially have a specific amount of load on one switch or one interface member pair, but then less load, I mean up to 90% load on one interface versus the other interfaces. And this doesn't even take into account the whole concept of a layer 3 ether channel when we're doing Cisco Express forwarding, because that can get even worse. Now, that being said, what happens if, for example, I decide that I want to have an uneven number of channel group members, right? So let's say instead of 4 interfaces in my Ether channel, I decide to only place 3 interfaces into my Ether channel. What is the effect of that into the Ether channel? What is the effect of that based on the algorithm that we've chosen? Right? As far as the XOR operation, it's pretty much the same, regardless of how you decide to match the pairs, whether it's MAC address or whether it's port number, whatever it might be, right? You have all these different options with regard to what I want to choose. One of the options that's missing here that's available on some of the more modern switches is source destination port, where you can actually look at layer 4 port information. So what happens if I only have 3 devices in the Ether channel? Well, guess what's going to happen? I have 3 interface members, but I'm using binary to represent the interface indices, right? So that means I can't just have 3 interface indices. All right, so now I've got gig 01, for example, and gig 02, and then finally gig 03 that are part of an Ether channel. What's going to end up happening is that one's going to get assigned index number 1, this one's going to get assigned index number 2, and then this one's going to get assigned index number 3 and 4, because we have to use them all. Our XOR operation can't say, okay, let's not take into account some of those bits or some of the XOR results because we only have 3 interfaces. So you might end up with a 1:1:2 type of ratio. And again, that's not load balancing ratio, that's just index ratios, right? So we've got one index on gig 01, 1 index on gig 02, and then 2 indices on gig 03, which might work out depending on your load balancing algorithm and what you decide to do with your load balancing algorithm. So for example, 0, 0, 0 would be 1, and then 0, 1 would equal 2, and 1, 0 would equal 3, and finally 1, 1 would equal 4. So it says this is where the challenge really comes into play, right? Because one of the things that you have to consider when you're defining the load balancing algorithm, and again, this is probably not something you're going to have to do on the exam because it's just on the lab exam, because it's just too, I think it's too complicated even for the CCIE lab to define this. But on the written exam, they might ask you some sort of question like, we're sending traffic, they'll give you a topology diagram. I'm sending traffic from this client to this server, and all the traffic is going over one link. But the client is using the server for FTP, and it's using the server for web traffic and everything else. My algorithm right now that I'm using is source destination IP. Naturally, that's going to go over one of the interfaces. What method could I use to fix this problem? And you would choose, of course, port number, because MAC address is not going to resolve the problem. I guess my point is, when you're going through the process of defining what load balancing algorithm you decide to use, you need to keep in mind what the traffic looks like. All right? If you see a lot of traffic coming from one source and going to one destination, but that traffic is using a lot of different port numbers, then you might look at some sort of layer 4 algorithm or layer 4 process. If you see a lot of traffic that's coming from a lot of different MAC addresses, right? In internal LAN traffic, that would be the case typically. But if you're continually talking to a gateway to go out to the internet, then a source and destination port might be your best option, because the destination MAC address is always going to be the gateway across that layer 2 domain. So I can't really say what would be a best practice. as far as which algorithm to implement, it really depends on the traffic flow and what's happening in your topology and how you're managing that traffic flow in your topology. That's going to truly determine, what the best algorithm is. All right. Couple of things I want to point out as well. The load balancing method is only locally significant to the device, and it's only outbound, of course. It's not going to affect any traffic coming in. It can actually be independently configured as well, which actually brings up a whole different aspect or twist to performing the best possible load balancing. We're not concerned in this case with asymmetric processing, like we would typically be with a routing process, where I want to make sure that my routed traffic goes one way and comes back the same way because my security might be blocking traffic, or I might be doing some sort of stateful inspection or whatever. We're talking essentially about a physical peer-to-peer type of connection. So you may decide to use one load balancing method going out, but a different load balancing method coming back over that particular Etherchannel link, because that's going to provide you the best possible load sharing capability. Does that make sense? The fact that the load sharing method is mismatched on either side doesn't really matter. Okay? All right. And to avoid polarization, you definitely want to make sure that you're essentially kind of loading that traffic appropriately. Unfortunately, there aren't a whole lot of options that you have to really see what the load conditions are. I'm going to show you a couple of options that you have to see, essentially in real time how traffic is being sent across a link. And I'll demonstrate that concept when we get into the configuration section. So you may be able to identify whether or not your load balancing algorithm is adequate for whatever you're trying to accomplish. Okay. If we're doing load balancing based on MAC address, for example, the MAC addresses are going to be tied into the physical, not the physical port in this case, but the port channel port. A couple of other things before we wrap up this first chapter, this first discussion. The link aggregation that happens is completely independent of the port mode. So as long as it's consistent, as long as the group member interfaces have a consistent configuration, it could be a tunnel interface, it can be a layer 3 interface, it can be a trunk, it can be an access port. You can have all kind of individual configurations on the interfaces. As long as the member interfaces have the appropriate configuration, that's the main thing that we're concerned about. Okay? The biggest problem that I've seen, and this goes to what Mike was kind of asking about with regard to best practice. The biggest problem that I've seen with configuring Ether channels is always about the issues that you have with orders of operations. Obviously, we already know, or you may not know, but we'll definitely talk about it, is that all of the members within the link aggregation group have to agree on specific parameters. All right. If two members in a group are layer 2, then the other members in the group have to be layer 2. If the two members are running half duplex, then the rest of the members have to be running half duplex, and so on. The biggest problem I've always seen, and it's only a temporary problem because you can always kind of resolve it, is just the order of issues that you have by entering commands in a specific order. How you're creating the Ether channel, what steps did you take to create the Ether channel, and where did you apply the commands. So when we get into the configuration section in a little bit, I'll talk to you about the right path that you should take when you're going through the configuration itself. Okay? So that's our introductory section on Ether channel. We're going to do two more kind of very brief sections. They're not really that long. We've got about an hour left for our allocated time. If we go beyond that, that's okay. I don't have a problem with that. But I do want to wrap up Ether channel today for sure. So we're going to take a look at layer 2 Ether channel configurations. We'll look at all 3 different protocols and kind of identify some of the commands that we can use to troubleshoot and verify Ether channel operations. And then we'll take a really brief look at layer 3 because it's really not much different than a layer 2 Ether channel from the perspective of Ether channel itself. All right, so we'll wrap up this lesson. We'll see you guys in the next lesson.